In section 2.1, the topic is the tangent and velocity problems. Now the word tangent is derived from the Latin word tangens, which means touching. Thus, a tangent to a curve is a line that touches the curve. So in other words, a tangent line should have the same direction as the curve at the point of contact. Now how can this idea be made precise? Now for a circle, if you look at the figure on the left here, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once, as you can see here in the figure. Now, for more complicated curves, this definition is inadequate. So if you look at the figure on the right, it shows that two lines, L and T, passing through a point P on a curve C. Now the line L intersects C only once, but it certainly does not look like what we think of as a tangent. Now the line T, on the other hand, looks like a tangent, but it intersects C twice. Now to be specific, we're going to look at a problem of trying to find a tangent line T to the parabola y equals x squared in the following example. Okay, now what we want to do is we want to be able to find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So if we investigate here, we can see that this represents the point 1, 1. Okay, so we'll go ahead and then plot that on our graph, point 1, 1. Okay, and now what we want to do is we want to be able to find an equation of the tangent line T, okay, as soon as we know its slope. Okay, but before we do that, all right, we need to pick some sort of arbitrary point here or anywhere on that curve. Okay, so I will go ahead and label these 2 points. This line, it'll just be green here, okay? Now, the green line, okay, is intersecting the graph at 2 points. Okay, now remember that the definition of a tangent touches it once. So when it intersects the graph more than twice, we call this a secant. Okay, now the difficulty is that we know only one point in this scenario, which is 1, 1. Okay, now whereas we need 2 points to compute the slope. But since we have our equation, okay, y equals x squared, then we can arbitrarily say that this point, we can call it Q, and if the input would be x, well then the output, which is the function x squared, would be x squared. So now what we have is we've determined 2 specific points. Okay, now in this scenario, we want to be able to find out what is the general slope formula, meaning like what is the slope of PQ, because that's what we want to find. We want to find the slope of PQ. So I'm going to go ahead and write down the general form for that. So we got to use our slope definition. So remember that's y2 minus y1 over x2 minus x1. So y2 in this case is x2, and then we're subtracting y1 all the way over x2 minus x1. So therefore that is our general, okay, slope form for this particular equation. Now we have to make sure that x does not equal 1, because in this scenario it would make it undefined. Okay, and we also need to make sure that q would not equal p. Okay, so again, that is our generalization of this particular equation. Now, if you notice here, this is where the value of 1 is located. Okay, and so we have values that go in between 0 and 2, but it keeps going because this is our x-axis and this is our y-axis. Now, what we want to do is, since we know the point is 1, 1, and it's starting at 1, we want to figure out, okay, from the left side, we're going from 0 to 1, and then from the right side, we're going from 2 to 1. So what's happening here? Well, what we can do is we can pick values in between 0 and 1, and pick values in between 1 and 2, and then determine what's happening with the slopes according to this point 1, 1, since that's what's given. So if we take the value of 2, okay, and use that as our first point of x. Okay, let's go ahead and do that. We're going to let x equal 2. Okay, now if we plug that into our function, then that means that y would equal 2 squared, which would then be 4. Okay, so now we know that we have this ordered pair 2, 4, and what we're going to do is we're going to compare it to the slope with our point 1, 1. So let's go ahead and do that. So for the first one, we want to be able to find the slope when we pick 4 to be y2 and 2 to be x2. So we end up with 4 minus 1 over 2 minus 1, which gives us 3 over 1, which is equal to 3. Okay, now as you can see up here, okay, when the value of x is 2, we determined that the slope equals 3. Now, let's go a little closer to 1. So as we're going closer to the point 1, we're moving now inward. Okay, so the number in between 2 and 1 is 1.5. So similarly, okay, if we want to use 1.5, okay, we'll go ahead and do the same thing here. If we choose x to equal 1.5, then we know that when we substitute 1.5 in for x and then square it, okay, it's going to give us a value of 2.25. So now, to find this slope, we're going to use those points. So we got y2 to be 2.25. So we have 2.25 minus 1 over 1.5 minus 1. Okay, and then what that's going to do is that's going to give us a slope of 2.5. So again, you can see here in the next one we get 2.5. Okay, now you should be able to see the pattern now for what's happening. Okay, again, if we choose 1.1, okay, let's go ahead and do that. So if we let x equal 1.1, and then we're going to pick y to equal 1.1 squared. And again, 1.1 squared gives you 1.21. So now we're going to use the order pair 1.1 and then 1.21. Okay, so now we're going to find the slope of this. And so we end up with 1.21 minus 1 over 1.1 minus 1. And now we're going to get a slope of what? 2.1. Okay, so as you can see, if you look here, as x, okay, gets closer and closer to 1, the slope is getting closer and closer to what? 2. Okay, now let's look at this other table here. Okay, so again, this is going from the value of 2 approaching the value of 1 because 2 is going to 1. Now what happens on the other side when we're going from 0 to 1? Okay, well let's take a look at that. So now if we look at this table here, okay, and we're going to let x equal 0. So if you plug in 0 for x, then y is going to be 0. So you're going to have the ordered pair 0, 0. So let's find a slope of that. So finding the slope using those 2 points is going to be 0 minus 1 over 0 minus 1, which gives you a positive 1. So you can see what happens with the slope when the value of x is 0. Okay, and let's do one more. Okay, let's see what happens when it's equal to 0.99. So when x is equal to 0.99, okay, y is going to equal 0.99 squared, which is 0.9801. Now again, finding the slope of that, you get 0.9801 minus 1 over 0.99 minus 1. And then that's going to give you a slope of 1.99. So what it's saying here is now is that as x, which starts at 0 and it gets closer and closer to the value of 1 on the left side, okay, then the slope then eventually is becoming 2. So what that means is that we want to be able to find a line, okay, now hopefully my line shows it a little bit better, but we want to make sure that it touches, okay, the graph once. Now remember, when it touches the graph once, that's going to tell us that it's tangent to that line. Okay, so what we've determined from making our tables is the fact that our slope is equal to 2. So by looking at those two tables, it's approaching 2. So we can say that our slope is approaching 2. Okay? And then what we're going to do is the given point was 1, 1. So now that we determined that it's approaching the slope of 2, then we can use our point slope form to find the equation of that line. So we'll have y minus 1, which is equal to 2 times x minus 1. And then solving for y would give us y is equal to 2x minus 1. And therefore, this is the equation of the tangent line through 1, 1. So let's take a look at Desmos here. This is the equation 2x minus 1. And so what I've done is, okay, I've graphed the parabola x squared. Okay, and what we want to do is, let's see what happens when we graph. Hopefully it allows us to do that here. So we're going to graph 2 x minus 1. And so now what you can see here is that this graph is intersecting and it's a tangent, so it's touching only once on this parabola. All right, so let's move on to the next illustration. Now, before we move on, I want to show you an animation. Okay, so again, the tangent line to a curve at a point P is defined to be the line through P whose slope is the limit of slopes of secant lines PQ as Q approaches P along the curve, and therefore as H approaches 0. So remember, this was the example that we had. It was kind of similar to this, okay? And so we can look at different functions up here, but since we just looked at x squared, we'll go ahead and look at x squared. Now, what we want to do is we selected the function which is x squared, okay? And then what we're going to do is down here, okay, this slider A, okay, is going to, it's the number above the slider to select a point on the curve at x equals A. And it's indicated by that red dot. So that means that everything along the x-axis that we're selecting is in red. Now likewise, okay, we're going to use the value of h with an h slider to observe the effect on the secant line shown in the graph. Okay, and again, that's indicated by the blue line passing through the red and blue dots when the secant checkbox is selected, which it is up here. Okay, and note that the secant slope is not defined when h is 0. Okay. All right, so as you can see here, if we look at this, this is a secant line, right? This is secant still intersecting 2 points, and then eventually when it's there, now it's intersecting it at 1 point. Okay, if we move the value of A, let's say over here, and then we have our secant. So there's our secant line. It's still a secant line, and then eventually when it gets to the point, then we know that it's touching it only once, which is therefore given as our tangent. Now again, remember here that h is undefined, and I also want you to point out here is that we're using these 2 points, okay, along with the point that's selected for the x-axis and the y, and by using the rate of change, that gives us our slope. Now you can turn the tangent and secant lines on or off by clicking the appropriate checkboxes, but you will see a checkbox to display a secant triangle which illustrates the values used in the computation of the secant slope. So if we selected that, okay, what's going to happen is that you're going to see this secant triangle, and then we'll discuss a little bit more of that in class, but we'll talk about what that means. So it creates a right triangle, and we'll explore a little further when we're in class. Okay, so that brings me to illustrating the limiting process that occurs in this example. So as Q approaches P along the parabola, okay, the corresponding secant lines will rotate about P and approach the tangent line. So you got to see here is that this point Q keeps getting closer and closer to P, and once it gets closer and touches P, then it becomes a tangent line. Okay, now in example 2, we're going to be estimating the slope of a tangent line from experimental data. The flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is set off. The data in the table describe the charge Q remaining on the capacitor, measured in microcoulombs at time t, measured in seconds after the flash goes off. Now we're going to use the data here that's given in the table to draw the graph of this function at the point where t is equal to 0.04. Note that the slope of the tangent line represents the electric current flowing from the capacitor to the flashbulb, which is measured in microamperes. Okay, now if you notice here, again, we're investigating at when the value of t is equal to 0.04, which is right here. Okay, and so now it creates this point on our graph here, and we can see that this point then has an output of, over here, 67.03. Okay, so now, since that is the point that we're going to be using, so the point that we're selecting here is when x is 0.04 and the output is 67.03. Now again, these are data values that's been given to us. Okay, so if we want to pick some point on this particular graph, okay, we can then find the slope. But we don't have an equation in this example. We have other points in the table that's given. So what we can do is we can pick another point here at the beginning. So that's this 0, 100. So we can use that point to then determine what is the slope of that. Okay, so if this is P, we can call this point R. And what we want to do is we want to be able to find, okay, what is the slope of that line? So we're going to start out here and write down the slope of PR. Okay, we have our y1, which is 100, minus y2, which is 67.03. And then we're going to divide that by x2 minus x1. And that gives us a slope of negative 874.25. Okay, so you can see here that that gives us the slope when we're using the point 0.00, 100.00. Okay, now we can continue to do that to find the slopes like we did in the previous example by using these other points, okay, to determine what is the slopes for each one. Okay, but what we want to do is that the table at the left shows the results of those similar calculations for the slopes of the other secant lines. From this table, we would expect the slope of the tangent line at t is equal to 0.04 to be somewhere in between negative 742 and negative 607.50. So if you take a look here, okay, look at the x values. Well, the x values here is at 0.02 and this is 0.06. So that means that 0.04 is in between those two values, which means that the slope would have to be in between negative 742 and negative 607.50. So what that means is that we can actually find the averages of those two slopes of those secant lines. So we're going to find the average slopes of the secant lines when x is equal to 0.02 and x is 0.06, because again, we note that 0.04 is in between those two values. So if we need to take the average of that, the average, okay, is basically saying, well, we're going to take the slope, negative 742, and then we're going to add the slope of 0.06, and that was negative 607.50, and then we're going to divide that by 2, or we can take half of that. And so then we're going to get the slope here to be negative 674.75, which is approximately negative 675. So what we've done is we determined that we estimated the slope of the tangent line to be negative 675. Okay. Now, another method, okay, that we can do is by drawing an approximation to the tangent line at P and measure the sides of the triangle ABC. So here we create a triangle, right? Okay, and so remember that the tangent, okay, is equal to the value of what? Y over X. Okay, so we're going to look at the side AB and then the side BC. Okay, so again, this represents our Y, right? When we're talking about the definition of tangent, okay, over X. So what do we know? Well, we know that since this is going down, the slope is going to have to be negative. So we know it's going to be negative, okay, regardless. Now, we also know that here, okay, we'd have to make sure that this distance is positive and this distance is positive, because regardless, it's going to be a negative slope. So we need to take the absolute value of whatever the distance is of AB and then divide that by the distance of BC. Okay? Now, how do we determine that? Well, again, we know that it's going to be negative. Okay, and what is the distance from A to B? Well, in this case, if we take a look at this triangle, okay, if we look at that point and determine what is the value here, well, it would be at 80.4. It's one way of being able to determine that. So looking at that point where that triangle is, you got 80.4. Okay, and then you're going to subtract what the distance here is, which would be 53.6. And then we're going to then find the distance between these two. And so the distance would be 0.06 minus 0.02. And so then we get approximately negative 670. Okay, now again, we are estimating the slope of this tangent line, so it should be pretty close to negative 675. So yeah, it's off about 5 units there, but they are pretty close. Okay, so the physical meaning of the answer in this example is that the electric current that's flowing from the capacitor to the flash bulb after 0.04 seconds is about negative 670 microamperes. Okay, let's take a look at example number 3, which is the velocity of a falling ball. Now, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above the ground. And what we want to do is we want to be able to find the velocity of the ball after 5 seconds. All right, so through experiments that are carried out 4 centuries ago, okay, Galileo discovered that the distance falling by any freely falling object is proportional to the square of the time it has been falling. Now, this model for free fall neglects air resistance. Now, if the distance fallen after t seconds is denoted by s of t and measured in meters, then Galileo's law is expressed by the equation. So this is a given information that we're going to need to know when we're talking about velocity of a falling object. So you want to make note that we're going to call s of t to be equal to 4.9 t squared. Again, that's a given information. Okay. Now, the difficulty in finding the velocity after 5 seconds is that we are dealing with a single instance of time, which is basically just t at 5. So no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second. So we can find out what's happening between t is equal to 5 to t is equal to 5.1. So since we're given, we want to find out what it is at t is equal to 5. We're going to explore the time interval of 1/10 of a second. So what happens from t is equal to 5 to t is equal to 5.1. Okay, so the average velocity is equal to the change in position divided by the time that has elapsed. Okay, so what we want to do is we're going to find out what happens when you plug in 5.1 into the function and subtract what happens when you put in 5 into the function. Okay, so again, because that's going to give you the change in the position over the time elapsed. Well, the time elapsed is going to be 5.1 minus 5. So again, you're using the rate of change here. Okay, so now substituting 5.1 into that function, so you're going to have 4.9 times 5.1 squared minus 4.9 times 5 squared. And 5.1 minus 5 is 0.1. Okay, and then when you multiply this all out, it's going to give you the value of 49.49, and that's meters per second. Okay, so if you take a look at this table, and this is our interval. Okay, similar to what we did in our previous example. Again, we were trying to find the values, okay, in a brief time interval of 1/10 of a second in between 5 and 5.1, and we determined at that particular point in time of that interval, the average velocity is 49.49 meters per second. Now, again, this table is showing the results of similar calculations of the average velocity that we have just done. Okay? It appears that as we shorten the time period, okay, the average velocity is becoming closer to 49 meters per second. So if we then shorten the time period here between 5 and 5.05, then you can see what's happening with the average velocity. Shorten it even more, and then even more, it's getting closer and closer to what? 49 meters per second. Okay, so what we can say then is that the velocity, okay, according to our table, at t is equal to 5 would be the following. We could say that the velocity is going to equal 49 meters per second. Okay, now you may have the feeling that the calculations used in solving this problem are very similar to those used earlier in the section to find tangents. Now, in fact, there is a close connection between a tangent problem and the problem of finding velocities. Now, if we draw the graph of the distance function of the ball, and then we consider the points, a 4.9a squared, and then q a plus h, we're adding h to the value of a, adding h to the value of a, okay, on the graph, then the slope of the secant line PQ would be the following. So it would be 4.9 times a plus h squared minus 4.9a squared over a plus h minus a, which is the same as the average velocity over the time interval in between a and a plus h. Therefore, the velocity at time t equals a, the limit of these average velocities as h approaches 0, must be equal to the slope of the tangent line P, which is the limit of the slopes of the secant lines. So here you can see the figures of what that looks like. Now, examples 1 and 3 show that in order to solve tangent and velocity problems, okay, we must be able to find limits. And so after studying methods for computer limits in the next 4 sections, we will return the problems of finding tangents and velocities when we get to section 2.6.